Hello guys, welcome back to my channel Gamma Die Gamma, and in this video I wanted to do a very nice question, and since it's gonna be done with complex analysis, so it's gonna be a legendary contour integration slash residue theorem video. So let's get started. Okay, so to give us motivation, let's define I to be integral from 0 to infinity of, let's take t now, t to the alpha minus 1. I mean take a if not alpha, over 1 plus t to the 2n dt. Okay, and now I would like to do this by complex analysis, so we need to define a complex function f of z, which I will define to be z to the a minus 1 over 1 plus z to the 2n, which is essentially the same thing, except I'm using a complex variable z in place of t or x or anything else. Now we need to define a contour for integration to take place over. So this guy over here, okay, so this guy over here is what's going to be our contour of integration. Okay, so I would just like to label a few things. This is the real axis, call this r, radius r. This is the origin 0, and this is the imaginary axis. And in this case, the angle might seem a little arbitrary at first, but it's not. Is pi over n. And the logic for this is you take the denominator, 2 pi divided by the power of the variable in the denominator over 2n. So you get pi over n, and you'll see in a minute why this trick works. Okay, now what I'm gonna do is before moving on with the contour integration step, which is gonna go from 0 to r and then path gamma here and then this path beta over here, I'm gonna call this alpha maybe. Before doing this, writing the loop equation for this, I would like to talk a little about the poles. So when is this function not defined? Well, when z to the 2n is -1, right? And -1, if you take the principal value, is e to the I pi. You can use Euler's formula for this. Let's call the pole z0. So z0 is e to the I pi over 2n. I mean, logically, or if you want to think about more generally, we would have to add another factor of say 2k pi, because the sine and cosine have a period of 2 pi. So to be more general, we would need to add that. But the thing is, this point is actually going to be over here at which has a radius of 1 and subtends an angle of I pi over 2n with respect to the real axis. It's basically going to be half away in the contour. And as I said, the general solution would imply e to the I pi over 2n plus 2k pi, where k is some integer that includes 0 as well. But the thing is, this point, for say k equals 1, k equals 0 is just the basic pole we have. For k equals 1 and higher values, if you see about it, it's anyways going to come back over here. It's going to be the same point. It's not like for k equals 0 we have this, for k equals 1 we have something else, k equals 2 we have something else. it's essentially going to be the same point. You're just calling it different things as you keep rotating in a circle around the complex plane. So there is only one of these that we need to take into account. I mean, you can take either. You could have taken for an arbitrary k equals, I don't know, 256, and that would still be a pole and that would still be valid for our residue theorem. But just to make, computations easy, let's stick with this one pole. Okay, that's the discussion about the poles. Now moving on to our loop equation. So the contour integral of f of z dz, and the contour is defined above, is going to be integral from on path alpha f of z dz plus integral on path gamma f of z dz plus integral on path beta f of z dz. Now on alpha, the z is going to be, just equaling x because there is no imaginary component to it. And we go from 0 to r. I'm just substituting using the parameterization f of x instead of f of z. That will imply x to the a minus 1 over 1 plus x to the 2n dx. Now we're gonna just, not do anything with gamma for now. Look at beta. On beta, the parameterization that's gonna work is z is going to equal to x times e to the I pi over n. Multiplying by this factor of e to the I times some angle is basically rotating the real axis by that angle. And that's precisely what's happening here. I mean, the figure isn't to scale, but you can see that every point on the x-axis is basically being projected sort of, or rotated if you want to think about that, on this by an angle of pi over n. So we're going to use that substitution over here. And notice we're going from r to 0. We have x times e to the I pi over n raised to a minus 1, and then there's another e to the I pi over n because of the dz is equal to this dx, divided by 1 plus x times e to the I pi over n, but the whole thing raised to the 2nth power. And then this other guy that we're not going to bother substituting first. Well, fine, just keep this as it is. Integral from 0 to r, x to the a minus 1 over 1 plus x to the 2n dx. We can have a negative, flip the upper and lower bounds. Well, one of this cancels with one of this. We have e to the I pi a over n, and this x to the a minus 1. Divided by 1 plus x to the 2n, and we have e to the I pi over n times 2n. So the n's cancel out. We have e to the I times 2 pi. So e to the I times 2 pi can be expressed as cosine of 2 pi plus I sine of 2 pi, which is precisely equal to 1. Cosine 2 pi is 1. This will become 0. So we don't need to bother about that at all. Like, it just vanishes, becomes 1. And that's precisely why we chose a contour like this, using this trick over here to choose the contour angle. That's so that, when we take make a parameterization on this second branch, when we are returning to the origin, we get the same denominator as before. Because now we can club the integral over alpha and the integral over beta terms together. They have the same numerator and denominator, and this is just a stupid factor which can be factorized out. 1 minus e to the I pi a over n. We can factorize stuff from this, and we have integral from 0 to r, x to the a minus 1 over 1 plus x to the 2n dx plus integral over gamma f of z dz. Well, that is precisely the value of contour integral of f of z dz. Okay, now let's look at this integral over gamma. And if you've seen my previous videos, you know that we have to use some estimation lemma, or more generally Jordan's lemma. Let's see what's going to happen. See you on a fresh page. Okay, given this contour, we have to look at integral over gamma of f of z dz. But I would like to consider the modulus of this guy, which is less than or equal to integral over gamma modulus of f of z. And by Cauchy-Schwarz, I can split the modulus over these. Okay, now I would just consider parameterizing everything. So z is going to equal to r times e to the I theta, and there theta is going to go from 0 to pi over n. That's the parameterization to work with. So integral from 0 to pi over n. We could have substituted f of z. I can write it down again. Z to the a minus 1 over 1 plus z to the 2n. So instead of z, we have this parameterization to put. So r times e to the I theta to the a minus 1 divided by 1 plus r squared e to the 2i n theta. This will become 2n actually. dz is ri e to the I theta d theta. Don't forget the mods. Okay, so now this, well, the e to the I theta times any arbitrary shit is just going to become 1, the modulus in modulus. So we precisely have r to the a minus 1 and this r cancelling out with a negative 1. So we have r to the a. Well, I and e to the I theta will have a modulus of 1 again. In the denominator we have, well, the modulus of this guy. So r to the 2n e to the 2i n theta plus 1 d theta. Now we can use a triangle inequality in the bottom, and we get modulus of this guy, which will just be r to the 2n. The e to the I times any stuff is just going to become 1 modulus. We have a minus 1 because of triangle inequality. Fair enough. Fine. This will be, you can solve this integral. Nothing depends on theta, so pi over n. These were just constants with respect to theta. And this was precisely mod of integral over gamma of f of z dz. I would consider taking the limit as r goes to infinity. And notice that to solve this, for this limit to exist, the denominator has to be larger than the numerator, because let's see, if you keep doing L'Hopital's rule, you're gonna end up with, say, a minus 1, 2n, r to the 2n minus 1. This is gonna cancel out. So you see, this process is going to basically repeat itself until, the condition is the denominator, the power on the denominator should be strictly greater than the power in the numerator. That's when the denominator becomes really large, and this entire integral goes to 0. Only if this condition is satisfied will this thing go to 0. So this is a pretty necessary condition, you know. Instead of just saying that, well, this function should converge or should not blow up, that's why the denominator powers have to be less than the numerator power. This is actually a little better way of showing all of this intuitive sense that we usually think of functions, especially in improper integrals on infinity. Okay, so this is a necessary condition, and if this holds, we have 0, and we are assuming this holds, otherwise the integral doesn't converge. So that's a nice sanity check there, which means this guy is 0. It's precisely 0. So after you take the limit, this guy will go to 0. That's what the entire Jordan's lemma, or you can call it estimation lemma, is saying in this case. So now we know that if we take the limit as r goes to infinity, this integral over gamma goes to 0. So let's do that on both sides. This guy will go to 0. Just keep this as it is. This guy will just become 1 minus e to the I pi a over n. The r will change to infinity. The integral from 0 to infinity of this f of x, which is precisely I. I've just changed the variable from t to x, which doesn't matter in definite integration. So this is just I. Fine. Now, you know, even if we don't write this as a limit as r goes to infinity, it's fine, because the contour will, you know, automatically get defined that way. Okay. Now it's time to do the residue theorem step. See you on the fresh page. Okay, so this was a contour with an angle of pi over n, and the residue was at pi over 2n. So the pole, I meant the pole, not the residue, z0 was at e to the I pi over 2n, if I'm not wrong. So now for the residue theorem, what the residue theorem says is contour integral of f of z dz on this same contour. And now, I mean, that's why I didn't write the limit as r goes to infinity, because now we're considering the infinite contour, like the contour with r tending to infinity. So that's captured in this notation. 2 pi I times the sum of residues inside this contour, since there's just one. So if 2 pi I, and for the residue, we have to actually do a limit as z goes to z0 of z minus z0 times f of z. So limit as z goes to z0, z minus z0. Well, f of z I can just substitute directly as z to the a minus 1 over 1 plus z to the 2n. I can make a substitution for z0 as well. Z goes to e to the I pi over 2n, z minus e to the I pi over 2n, z to the a minus 1 over 1 plus z to the 2n. Now notice that as z goes to e to the e raised to I pi over 2n, the denominator will go to 0, because that's the definition of the pole. That's how we calculated the pole actually. And then even this term will go to 0. So we actually can work with L'Hopital's rule. So if we differentiate the top and bottom, at least these terms, these other terms, because this guy can just directly be expressed as e to the I pi over 2n raised to a minus 1. These are the trouble making terms, right? This and this guy. we can take this thing out. So when we do L'Hopital's rule, this guy will just go to 1, and we are just left with limit as z goes to e to the I pi over 2n of 1 over 2n times z to the 2n minus 1. So we can cancel out some 2's. We have I pi over n and e to the I pi over 2n a minus 1 over e to the I pi over 2n raised to the 2n minus 1. So this guy cancels with this. We have I pi over n e to the I pi a over 2n divided by the 2 pi's cancel. E to the I pi is negative 1. So this finally becomes negative I pi over n e to the I pi a over 2n. And that is precisely the value of the contour integral f of z dz by the residue theorem. Okay, now we know what the contour integral equates to, and we know what each part of the contour equates to. So now let's basically just tie everything together. Okay, so we got this from the page 1, which was about the contour. This we got from the second page, which was to do with residues. So now let's equate both of them. We have 1 minus e to the I pi a over n times I is equal to negative I pi over n e to the I pi a over 2n. So I is equal to, now we can use the negative to flip the order of this. I pi over n e to the I pi a over 2n, and then flip the order, e to the I pi a over n minus 1. And now what we're going to do is we're going to use this, write this as a negative power in the denominator. So when we do that, we have e to the I pi a over n minus I pi a over 2n minus e to the negative I pi a over 2n so we have I pi over n, and this becomes 1 over e to the I pi a over 2n, this is basic addition, minus e to the I pi a over 2n. Now I would like to do a clever thing. I would like to multiply and divide by 2i, because if you remember Euler's formula, this is negative by the way, sorry. If you remember Euler's formula, actually sine theta could be expressed finally as e to the I theta minus e to the negative I theta over 2i. That's why I multiplied and divided by 2i, because this I cancelled with this, pi over 2n, and this just becomes 1 over sine of whatever the thing was, pi a over 2n, and sine, 1 over sine can properly be expressed as the cosecant of pi a over 2n, and that's precisely the value of our integral, because I was integral from 0 to infinity t to the a minus 1 over 1 plus t to the 2n dt. And this result, and this is what's nice about this guy, because we can apply this result in many different ways. You'll see in some of my upcoming videos how I apply this, and it's a really powerful thing. It's a really nice thing. The best part is I've written it in a general form, so you can plug in anything you want and you get the result. So I hope you enjoyed this video, because I believe in my opinions, for at least the recent videos I've uploaded, this was a legendary video. So Please like and subscribe to my channel if you like the video. Thank you. Again, I urge you to like, share and subscribe to my channel because I want to hit my goal of 1000 subscribers. And thanks for watching. Stay tuned for more content. Signing off.